The next speaker is Andrey Piatnitski for his last talk in this course. So please, Andrey, go on.
Yeah, thank you. So two previous lectures, we use them to formulate and to prove the homogenization theorem for random elliptic operators. And in the proof, I provided all the details. Today, our plan is as follows. I'm going to first to show some examples of random media, because so far all the random media we discussed were introduced just through the action of some dynamical system in a very formal way. I think it will be nice to have some particular examples of random media. And then I will formulate without proof some more modern results in the this area of random stochastic homogenization. So let us start with some examples of random media. I don't want to discuss the examples which are obtained by random perturbation, typically small in the sense not too large perturbation of periodic media. That's clear. But I prefer to consider some examples which has nothing to do with periodic structure. So the first example is the Bernoulli checkerboard structure. So what is checkerboard structure? We take the integer lattice in RD, the lattice ZD, and to each element of ZD, we assign a random variable. And for simplicity, let us assume that this random variable takes on just two values. The value alpha with probability p, and p is some number between 0 and 1. The cases p is equal to 0 or p equal to 1 are not interesting. The picture is getting deterministic. So we assume that p is strictly between 0 and 1. And this random variable takes on the value beta with complementary probability 1 minus p. And what is important, we assume that these random variables are independent and okay, they are identically distributed just by construction. Also, we assume that they are independent. So this kappa j, we denote this, them by kappa j, they are IID random variables. And now we construct a unit cube centered at this at each integer point in RD, and having this value of kappa j at the center of the cube, we assign this value alpha or beta to the whole points in this cube. In this way, we obtain a random function which takes on two values, alpha and beta. We assume that both of them are positive, and just for definiteness, let's assume that beta is greater than alpha. Alpha is positive. And then we introduce the matrix A, just multiplying the identical matrix by this coefficient kappa j. This field, this matrix field, is invariant, is statistically invariant. Its distribution is invariant with respect to the integer shift, but not with respect to any shift in our RD. And you remember, we want to have a distribution which is invariant with respect to any shift in RD, not only with respect to the integer one. So there is a standard trick how to extend the invariance with respect to integer shift to the invariance with respect to an arbitrary shift in RD. We do the following. We introduce a random variable eta, which is independent of all these variables kappa, and which is uniformly distributed on a unit cube, on the unit cube, let's say it's the unit cube centered at 0. And then we do the following. We take our matrix, we evaluate our matrix, not at the point x omega, but at the point x plus eta omega. In this way, we spread this distribution, which was so far defined on unit cube centered at the integer point. We distribute the center uniformly over the unit cube. And this new distribution, which is a of x plus eta, depending on omega, is the desired stationary field. So this field takes on two values, and it's stationary, and one can prove, and it's nice exercise, not so simple in fact, but not difficult. It's using the fact that these variables kappa j are independent. One can show that this distribution is ergodic. This matrix field is ergodic. So we have all the conditions of applicability of our homogenization theorem. So we can claim that the elliptic operator with this matrix does admit homogenization. And the limit operator will be deterministic because we are in the ergodic framework. That's the first example. Another example, which is very popular in physics, in many mathematical models, is a Poisson point structure. So how do we construct? We will consider two examples related to the Poisson structure. Let P be a Poisson point process with intensity 1. What does it mean? Poisson process, by definition, is a measurable subset of Rd, such that in any bounded set, there is only a finite number of elements of this set. So, and the process is called Poisson. This locally finite subsets, measurable locally finite subsets of Rd are called Poisson point process if the following two conditions are satisfied. The first, the random variable, which is defined as a number of elements of Poisson point process in a given bounded Borel set Q, has a Poisson distribution. So the probability that this random variable is equal to some integer k is given by this expression, exponent to power minus volume of q times q to power k over k factorial. And this should be hold for any bounded Borel set. And the second condition, for any disjoint Borel sets Q1, Q2, and so on, Qn, the random variables characterizing the number of elements of our Poisson process inside this Qj are independent. So for any disjoint collection of Borel sets, these variables are independent. Now we construct our matrix field in the following way, random matrix field. We take a non-negative C0 infinity function phi, and we form the matrix, which is isotropic, which is proportional to identical matrix, and the coefficient is constructed in the following way. We take again two different positive numbers, alpha and beta, and take alpha plus sum of over all points xj from the Poisson point process, and of phi evaluated at point x minus xj. Since phi has finite support, almost surely this sum is always finite. it's written, it looks like an infinite sum, but in fact, in this infinite sum, only finite number of elements are not equal to 0. So finally, this sum is finite, this sum is also finite, it's the same sum. And as a result, we get a random variable here, random function here, and which depends on x. And it's easy to check since the Poisson process is invariant with respect to the shift, its distribution. Here we have also a function whose distribution is invariant with respect to the shift. So the stationary, statistically homogeneous distribution. Here it's a bit less trivial, the proof of the fact that it is ergodic, but it is ergodic. So again, we can claim that if we consider the operators with this divergence form operator with this matrix, then they admit homogenization and the limit operator is deterministic. Well, one more example, which use Poisson-Varanoi tessellation, also very popular construction in random geometry. We can take the points of Poisson point, we can consider the elements of Poisson point process and construct the Varanoi tessellation corresponding to this locally finite set. What we do, each Voronoi cell is just the set of points which are closer to xj than to all other points of the Poisson process. So each cell is defined as a set of points of Rd whose distance from xj is smaller than the distance to all other points of the process. And now what we can do, for example, we can take the volume of the corresponding cell, and inside this cell we can write the coefficient A as again some alpha plus Vj divided by beta plus the volume of Vj. This will be another stationary field, stationary because the Poisson distribution is invariant with respect to any shift. So it's a nice exercise to check that the matrix A defined in this way, I forgot to put the identical matrix here, that this is again a statistically homogeneous field. Well, in all these examples, matrix was isotropic. Of course, we can play a similar game and can construct a non-isotropic elliptic matrix, which also satisfies this condition. For instance, we can choose we can take two positive definite non-symmetric matrices and take random sum of these matrices with strictly positive coefficients or something like this. There are many different ways to construct these random functions. Well, the set of random fields in the collection of random fields in a sense is very rich. There are very many different examples and different constructions. So here I just show it two very popular construction. One is related to Bernoulli model, another is to Poisson point process. Well, now there was a question, and I think it's a good idea to give some comments about the non-ergodic case. In the non-ergodic case, the theorem that we proved in the first two lectures remains valid, with the only change that now the effective matrix need not be deterministic. It might be random. And in all typical examples, it is random. So in order to formulate the result, I'm not going to prove this result. And it is in fact the same, it can be proved in the same way as the result in the ergodic case. But what is important is that in order to formulate the result, we should introduce the sigma algebra of so-called invariant subsets. So if Tx is not ergodic, then the collection of invariant sets is non-trivial. So you remember that in the ergodic case, the only invariant sets up to the set of zero measure are empty set and the whole set omega, the whole space omega. Here there might be some non-trivial in non-ergodic case. There are some non-trivial measurable invariant sets. And the first exercise is to prove this statement. I leave to it as an exercise. It's in fact the proof is straightforward. Is the fact that the invariant sets form a sigma algebra. It's sigma sub-algebra of our algebra F. And we denote this sigma algebra by F invariant, F inv. Now, I hope you remember that we introduced this matrix of the, formally the gradient of characters, the matrix theta, which was a matrix with whose columns are potential vector field. And we introduced the character chi of x omega. So in non-ergodic case, this construction are exactly the same. There is no changes. We still can define this matrix theta and this character. And now we can formulate the homogenization theorem in non-ergodic case. So the problem star, you remember, it's a divergence form operator with right-hand side from L2 and with homogeneous Dirichlet boundary condition at the border of Lipschitz bounded domain. So it admits homogenization. Its solution converges to the divergence to the problem, Dirichlet problem for a divergence form operator with coefficient a home, which is constant in X, but which depends on omega and is defined as a conditional expectation of this expression, A, matrix A multiplied by the matrix theta plus identical matrix, and we take conditional as an expectation with respect to the invariant sigma algebra. The result is measurable with respect to the invariant sigma algebra, but it need not be a constant anymore. So up to this modification, the theorem states the same as in the ergodic case. In the ergodic case, the invariant sigma algebra is trivial, so conditional expectation coincide with just expectation. And so in the ergodic case, this theorem gives us just the theorem that we proved in the previous two lectures. So here I repeat that this stands for the conditional expectation with respect to the invariant sigma algebra. And the proof is essentially the same as in the ergodic case. There is no big difference. Well, now I proceed with some much more modern result, namely homogenization of non-local convolution type random operators. So what is non-local convolution type random operators? First, not random, but in general, what kind of operators we're going to study? So we say that the operator is of convolution type if it has the following structure. For simplicity, I will consider the operator in RD. I will make some comments on the operators in bounded domains, but let's start with operator defined in the whole space RD. So we consider some function alpha, which depends on the difference x minus y, and some lambda of xy, which is responsible for the local characteristics of the media. In a sense, if there is no this function lambda, then we say about convolution type operator with constant coefficient. A is just convolution kernel which defines the operator. So about alpha, we assume the following properties: that alpha is non-negative, alpha is such that it's integrable and its integral is equal to 1. This normalization can be changed. We choose 1 here just for the sake of definiteness. Then we will assume that alpha of z is equal to alpha of minus z, which makes the operator without lambda symmetric. And we also assume that lambda of xy is equal to lambda of yx. Under these two conditions, the operator A is symmetric, it's self-adjoint, it's bounded operator, so it's self-adjoint. And also, and this is a very crucial condition, we will assume that second moment of alpha are finite. So if we multiply alpha by modulo z square and integrate over the whole space, the integral should be finite. Well, and finally, we will need a uniform ellipticity condition. In this case, is this of this non-local operator, this ellipticity condition formulated in this way: that the function lambda, the coefficient lambda in the operator, is separated from 0 and from infinity. So it belongs to the interval lambda to power minus 1 lambda. And lambda is some positive number. I forgot to write here that lambda is positive. So that's the class of operator we're going to study. What we can show that under this condition, which were formulated, this operator A is bounded in L2, and it's nice exercise to show this. Well, and it's kind of trivial to show that it is symmetric. And moreover, this operator is non-positive. If we consider any non-trivial function in L2, then minus a applied to u in the product with u is strictly greater than 0. But we do not have uniform coarseness. So in order to make the problem well posed, we will make a spectral shift. We choose some arbitrary positive number, gamma, and we consider the operator A minus gamma, minus because A is negative. And then this operator A minus gamma is now invertible, and from this negativeness and from symmetry, it's easily follows, for example, by the spectral theorem, that the norm of the operator A minus gamma to power minus 1 doesn't exceed 1 over gamma. So the resolvent of this operator is bounded. Well, and now, so far it was just generic definition of this convolution type operators, and we consider it only symmetric convolution type operators. Now we introduce randomness in the same way as we did before. We say that we have given a standard probability space. We assume that this space is equipped with a dynamical system Tx. We assume that this dynamical system is ergodic. And we assume that lambda 0 of omega is a random variable. And then we define our function lambda of x, y, omega in this way. We assume that it has a product structure, lambda 0 of tx omega, lambda 0 of ty omega. No doubt that in this case, with the same function lambda, this function is symmetric with respect to x and y. Well, of course, instead of just product, we can consider any finite linear combination of products of this type with this positiveness condition, and the theorem also applies to this case. We can also formulate this theorem for generic function, but it requires some caratadori condition, because I first define lambda as a function omega 1 and omega 2, and then I should take the trace of this function. And since omega is a set of arbitrary structure, it's not clear what caratadori condition means in this case. So in order to fix this problem, we should assume that omega has a topological structure, and then we can define more generic kernels. But I don't want to spend time with this, because all the ideas will be clear with just the product structure. In the case of product structure, this problem doesn't appear. And we, for a while, will assume that we have lambda of x, y, omega defined like the product of lambda 0 of tx omega and lambda 0 of ty omega. Now we consider our problem to be homogenized. First, we consider the rescaled operator, A epsilon. So, of course, we use operator, instead of x, we use x over epsilon. Instead of y, we use y over epsilon. And then we write alpha of x minus y over epsilon. If you think about differential operator, we do the same. But then we have this strange factor, epsilon to power minus d minus 2. Where does it come from? Epsilon to power minus d comes from the Jacobian. When we make change of variable, we should compensate the Jacobian, and Jacobian is epsilon to power d. So in order to compensate it, we use epsilon to power minus d. So epsilon to power minus d is natural. But then also, for example, if we think about the parabolic operator for differential operator first, if we make change of variable, time is getting epsilon squared times old time, x is getting epsilon times old x, then on both sides we will have coefficient epsilon to power minus 2, which disappears because we can mutually cancel this epsilon to power minus 2 on both sides. The same thing here. The right, maybe I should comment it in more clear way. Let me show it. In the case of differential operator, we write d over dx is equal to epsilon d over dx over epsilon. But then we remove this epsilon, and we remove this epsilon, and this gives us the coefficient just 1. Here, since we don't have partial derivative, we cannot do this, and we should keep this power 2. And the result I'm going to formulate will justify that this power is correct. Then we fix positive gamma and consider the family of problems which are written here. So we, in the whole space, RD. We want to solve this problem A epsilon minus gamma u is equal to F. Since this operator is coercive, by the Lax-Milgram theorem, there is a solution, U epsilon, we call it U epsilon. And then we can formulate our homogenization, first homogenization result for non-local operators. And this result was obtained by Elena Zhizhina and myself in 2017. So if Tx is ergodic, then for any, almost surely, for any right-hand side from L2, solution U epsilon of this problem converges as epsilon goes to 0 in the space L2. It's not written here, unfortunately. It converges in L2 of RD to the solution of the following limit problem. So in the limit, we have differential operators. So divergence A home gradient U minus gamma U is equal to F. Here, A home is a constant deterministic positive definite matrix. So you see, it's quite nice. We started with the operators, which at least locally are compact themselves. And in the limit, we obtained the operator with a compact resolvent. Not exactly because we're in the whole space, but if we consider similar problem in a bounded domain, what I say will be correct. So we start with integral operators with integrable kernel, and we end up with operator which is differential, second order differential operator. Well, about boundary value problem. I prefer not to consider boundary value problem here because for non-local operator, boundary condition is a tricky thing. It's, for example, if we want to impose homogeneous Dirichlet boundary condition in some bounded domain Q, then we should assume that U is equal to 0 not only as a boundary, but everywhere in the complement to the domain Q, because the operator is non-local. So when we write down this integration over the whole space RD, and we have to do so, we will see the value of U not only as a boundary of the domain Q and inside, but also everywhere in RD. So boundary condition in this case is formulated in the whole complement to the domain Q. But up to this change in the definition of boundary condition, we can show that this homogenization result also holds in a bounded domain. And in the limit, we have the same differential operator as here, with in the limit with the standard Dirichlet boundary condition. So this non-local boundary condition in the limit will become local homogeneous Dirichlet boundary condition. I do not formulate this result explicitly, but I think it is clear. The limit operator is the same, effective coefficient is the same, and instead of this condition that U is equal to 0 everywhere in the complement of Q, in the limit we'll have just condition that U is equal to 0 at the boundary of Q. Well, now some philosophical, if you want, remarks. In fact, obtaining the effective matrix a home relies on constructing a corrector. Corrector technique applies here, and constructing a corrector is a rather non-trivial job. We spend a lot of time trying to understand how this corrector should look like. And the point is that in non-local problem, typically corrector technique doesn't apply because we have a function U. When we define the operator, we have function U defined at two different points, X and Y. So corrector is supposed to somehow compensate some discrepancy when we apply operator to function u, but this function u is evaluated at two different points. So it's not clear at which point this correction should takes place. Here we can use the corrector because you see in our family, let me show you one more time this problem, this operator which we try to homogenize. Where is it? It's here, I think. I put it somewhere, now I cannot find it. Yeah, here it is. Here we have this function alpha of x minus y over epsilon. And this function has a finite second moment. So this plays a role, this factor plays a role of localization. In the limit, only the points x and y, which are very close to the diagonal, contribute to the operator. So roughly speaking, we can define the corrector on the diagonal only. And this corrector will compensate the discrepancy both for the value of u evaluated at y and an x, because only the point x and y, which are very close to each other, contribute. And now I'm going to illustrate what I said with the homogenization result for another type of non-local operators, namely for non-local operators with singular kernels or Levy-type operators. Let me recall that the fractional power of Laplacian, there are several different representations for this operator. We assume that S between 0 and 2, so that S over 2 is between 0 and 1. So fractional power of Laplacian can be written in the following way: some normalization positive constant, and then the integral of over Rd u of x minus u of y divided by x minus y modulo to power d plus s. The domain of this is a self-adjoint unbounded operator in L2 of Rd, and its domain is just Hs of Rd. But this operator is somehow the prototype operator. It's an operator with constant coefficient. Now we want to consider the operator with variable coefficient. And it's natural to introduce it in the following way. We say that this operator with variable coefficient of Levy type has the following form. It's still u of y minus u of x divided by x minus y to power d plus s, but then we multiply it by some function which will satisfy ellipticity condition, of course, which depends on x and y, and we scale this function with the coefficient 1, the argument with the coefficient 1 over epsilon. And again, to avoid the problems with this Caratteodori condition, with this definition of the trace, we consider the simplest case when the function lambda has the product structure. So it's some function lambda 0 evaluated at the point tx over epsilon omega and multiplied by the same function lambda 0 evaluated at the point ty over epsilon omega. Well, let me just repeat briefly that as above, we have a standard probability space and the ergodic dynamical system. The framework is the same as in the previous cases, so I don't dwell on it. And what we assume that ellipticity condition is satisfied. So ellipticity condition, like in the case of partial differential equation, is crucial here. If we admit some even not uniform positiveness, but non-negativeness, it's the degenerate case, there will be immediately serious technical, and not only technical, serious problems. So we assume that uniform ellipticity condition is satisfied and consider this operator with this lambda, which has this product structure. And I said already that S is exponent between 0 and, which is between 0 and 2. So again, one can show that this operator is non-positive. So for gamma greater than 0, for any positive constant, this problem, which is written here, is well posed. Then it has a unique solution, and we denote this solution by U epsilon. So as usually in this homogenization theory, we would like to know what happens to U epsilon as epsilon goes to 0. In other words, we are going to show that this family of problems admits homogenization. Well, theorem. This theorem was obtained in the work by Maurice Kassmann, Elena Zhizhina, and myself in 2019. For any function f from L2 for D, the solution U epsilon converges strongly in L2 for D to a solution of the following homogenized problem. This is a problem with a constant coefficient lambda hom. So in the limit, we have just fractional power of Laplacian with some coefficient. What is lambda hom in this case? In this case, there is an explicit formula. We should take, you remember, lambda, our lambda has a product structure. We take the expectation of lambda 0, we take square of it, and this gives us this coefficient lambda hom. Now, in the case of product structure, we can consider also the operators which are not symmetric, in the sense that instead of the product lambda 0 of omega 1 and lambda 0 of omega 2, we consider different function. So let's consider a bit more general example, more general set of operators. So we have the function lambda 0 of omega, lambda 1 of omega, two different in general function, but we assume that both of them satisfy uniform ellipticity condition. So both lambda 0 and lambda 1 takes on values on the interval between two positive constants. So they are separated from 0 and from infinity. Well, here the operator is not self-adjoint anymore, so the well-posedness of this problem should be justified. But it's not, because it's a operator has a product structure, it's not difficult. We can just find the inner product, weighted L2 space, in which this operator is getting symmetric. And using this trick, we can easily show that this problem, which is written here, is well posed. It has a unique solution, and moreover, uniformly in epsilon, the solution satisfies this bound that U epsilon h s over 2 norm of U epsilon is uniformly in epsilon bounded. Well, and then another theorem from the same work states that as epsilon goes to 0, almost surely U epsilon converges to a solution of the operator, which formally looks in the same way as in the symmetric case, but the formula for the effective coefficient lambda hom in this case is different. So look, we should take the expectation of the ratio between lambda 1 and lambda 0. We take this expectation and we take this expectation to power minus 1. And we multiply this constant by the expectation of lambda 1 squared. Clearly, this constant is positive, strictly positive, and homogenization takes place for operator of this form, and if we have symmetric operator of more general form, let me write it here, if we have symmetric operator with lambda omega 1 omega 2 such that lambda omega 1 is equal omega 2 is equal to lambda omega 2 omega 1, and if we are able to make sense to the expression lambda of t x over epsilon omega t y over epsilon omega, then similar result holds for the kernel of this type, which is written in green. And the result will be just the expectation of lambda both in omega 1 or omega 1 and omega 2. So we should integrate this lambda in the probability space, first in omega 2, then in omega 1, and this will give us the effective coefficient. But the difficulty here is that in the general case, this guy is not well defined. We need some type of characteristic condition, so we should assume that our probability space has some topological structure, so that we, and that as the corresponding sigma algebra is a Borel sigma algebra F, and in this case we are able to introduce the characteristic condition, and then this guy makes sense. Well, I thought about giving some comments about some gamma convergence problem, but I think I don't have time for this. So
you have 1 or 2 minutes.
No,
or
1
a couple
or
of
2 minutes is not sufficient, so I prefer just
okay, you have
I say a couple of words about the estimates, because there was also some questions about the estimates.
Okay.
So just in words, of course, if we have only ergodicity, then we cannot expect any quantitative estimate, because ergodicity it's a qualitative property. So for generic ergodic media, we have convergence and nothing more. So the difference between the U epsilon and U0, the effective solution, it goes to 0 and L2, and that's it. But if we have some mixing property, for instance, if the maximum correlation coefficients decays polynomially, then we can obtain some estimates for the rate of convergence, but this is just some polynomial estimate with quite implicit exponent. This is a very old result of Urinsky of 1981. He showed that if as I said, if we have polynomial decay of maximum correlation coefficient, then the expectation of the discrepancy goes to 0 as epsilon to some positive power, which depends on ellipticity constant, on the dimension, and on the rate of decay of the maximum correlation coefficient. But unfortunately, he used in his work this Nash-George results for Gerber continuity. So the power which he obtained is very implicit. You cannot trace it. But recently, there was a series of works by Antoine Gloria and Felix Otta. And in the case of finite range of dependence, it's quite a restrictive case, but even in this case, there were so far there were no estimates. They have shown much better estimate, namely the expectation goes to 0 almost like square root of 2. It's square root of epsilon. It's it's epsilon to power 1/2 minus some minus delta. So it's very interesting collection of works for those who are interested in the rate of convergence. Well, I think at this point I have to stop. Thank you very much for your attention.
Thank you, Andrey. There are some questions.
Will the fractional order of the limit operator depend on the measure of holes? If the structure will be porous? Well, for perforated domains, there are results of perforation in perforated domains for the limit operator, and for fractional order, the power is the same. Only the coefficient will change. So in order to have different power, we should consider degenerate case. Either the geometry should degenerate or the coefficient should degenerate, and I'm not aware of any results of this type. But in the regular framework, if the media is dispersed, or if media is regular enough, and if the coefficients are uniformly elliptic, then the limit operator has the same power, or the same exponent as the original one.